why don't we start off with what is a planet, and we can start in our own solar system. Now, there's actually an international definition of what a planet is in our solar system, and there's three components to that. The first one is kind of obvious. It has to orbit the sun. An extrasolar planet, for instance, doesn't orbit the sun, so we don't call it a planet in our own solar system. And the second thing that's important to be a planet, or at least in our solar system, is it has to be round. So this essentially means that things like asteroids with weird shapes don't get to be planets. And there's a third one, and this is what really doomed Pluto a number of years ago, and that is it has to clear out its neighborhood in its orbit. So if there's something that's round and there's something nearby, and which is about the similar size, they'll call it hasn't cleared out its orbit, it's not the biggest one on the block, and it doesn't get to be a planet either. So with those three things that define what a planet is, we have 8 planets in our solar system that we're quite familiar with, like Mars and Jupiter.
Recently, it was the early 90s, we actually discovered examples of planets orbiting stars other than the Sun. And we call these extrasolar planets or exoplanets. And really, before that point, we did have quite a diversity of sort of planets, if you like, in our own solar system. We had small rocky bodies that were close to the star, and then we had sort of colder giant bodies a bit further out. And these things spin at different rates, and they're heated differently. There was quite a diversity. And it wasn't until we really discovered exoplanets that this exploded. And now what we found is over 2,000 exoplanets, and actually they cover a huge range, a really exotic range of sort of parameters or climates or types, if you like.
We found thousands of extrasolar planets outside of our solar system, and many of them do resemble some of the planets we have here on our own solar system. For instance, we found planets with the same mass and the same orbit and the same size as Jupiter. So these are Jupiter analogs outside of our own solar system. And we've even found planets which have the same radius and the same mass as our Earth. Now, these planets actually orbit quite close to their star. We haven't found an actual Earth twin, but they are the same size and the same masses as the Earth. So as far as masses and size, they very much can resemble the planets in our solar system. There's a lot of extrasolar planets out there. There's probably more planets than there are stars in the sky. So, and a lot of the most common types we actually don't have in our own solar system. So for instance, hot Neptunes, planets which are like Neptune but orbit very, very close to their star and are heated to thousands of degrees Kelvin. Or super Earths, planets which could be even twice the size of the Earth and still made of rock, but then 17 times more massive. And even on extreme orbits, like orbiting very close to their star. So these are very extreme, in our point of view, planets, but they're actually very common outside of our own solar system when we have no analog. Things like this weren't even dreamed of before planets were discovered.
So just to give an example of that, this is a scale model, or a football, otherwise known as, and this is a typical size of the Sun, if this was the size of the Sun. This is a typical size of a large exoplanet, something that's sort of slightly bigger than Jupiter. And we found these objects very, very close to their sort of parent star. So they're very hot and blasted, and that's completely different to the planets we have in our solar system. So very quickly we learn that our solar system isn't really a prototype. It's not a sort of basic template of how planets work or how planets are structured. And then of course we have a huge range, even in our own solar system. If we take the ball here, and then there's a small bead in my hand, which is probably quite hard to see. This is probably this would be the scale size of Earth in comparison. And we've still found that same range of sizes and types of exoplanets, but we found them in very, very different locations. So again, very close to their parent star or much further out, and across a huge diversity. Having said that, there are similarities that we can draw that can help us to understand these planets. We do find planets similar to Jupiter in similar orbits, and we're beginning to find planets that are similar to Earth in sort of size and radius, and then hopefully eventually also in the kind of heating that they experience or their atmospheres as well.
Well, let me illustrate a bit about a hot Jupiter. So if this football here is a star, this ball here is a scale model of what one of these hot Jupiters is. In this case, a well-studied hot Jupiter, WAS-12. So in just a scale, they would be about this far apart, only 3 or 4 times farther away from the actual star than the size of the star itself. And just to give you a sense of scale, if we put Mercury in our scale model here, Mercury would be on the other side of a large room. And if we actually put our own Jupiter in here, it would be a football field away. So this planet is really close to its star. And because of that, it's heated to thousands of degrees Kelvin on the day side, just being blasted by the radiation from the star. And because it's so close, it orbits in only about a day. So 1 year on this planet is only 1 day, whereas Jupiter takes over about 12 years to orbit the sun. So these are very extreme planets with very extreme conditions.